Hi, my name is Neha Pawar, and I'm an engineer at StarTree.
I'm Xiaobing, also come from StarTree.
And we are here to tell you about how we added tiered storage for Apache Pinot in StarTree Cloud, thus enabling the speed of Apache Pinot at the cost of cloud object storage. So I'll be kicking things off here. I'll first talk about the motivation and give a high-level overview. Then Xiaobing will come in and tell us about the performance optimizations that we did. And finally, I'll wrap things up by talking about some future enhancements that we are up to.
Cool. I'll see you in a minute.
See ya. We'd like to start this talk with one important question that many of us must have faced being in data engineering. Your organization is collecting a lot of data. Some of it might be real-time, some of it might be batch processing. You're keeping all this data for long periods of time. And now you need to make sense of this data and also help your customers and users make sense of this data. So we need some analytics infra. Your organization wants to use the historical data for doing report generation, internal metrics dashboards, ad hoc analysis, and also use the real-time data slightly differently to provide real-time analytics, do anomaly detection, create some real-time user-facing analytics applications. Now, as a data engineer or a decision maker for the data org, you are tasked with choosing this infra. The considerations on top of your mind are cost, performance, and flexibility. You need systems which will be able to service the different workloads while maintaining the query freshness and latency SLAs needed by those use cases. The other aspect is cost. You need a solution where the cost to serve is reasonable and the business value extracted justifies that cost. Lastly, you want a solution that is easy to operate, to configure, and also one that will fulfill a lot of your requirements together. Now, for serving real-time data and user-facing analytics, you will typically pick a system like Apache Pinot. There's also other open source as well as proprietary systems which can help serve real-time data, such as Druid or ClickHouse. Why are these systems able to support real-time low-latency analytics? One of the main reasons is because they have tightly coupled storage and compute. The compute nodes use disk or SSD to store data. The disk SSD could be on local storage, or it could be remote attached like an EBS volume. With both of these, you can use POSIX APIs and use techniques like M-mapping your data onto them. As a result, accessing them is super fast. The access speeds for local storage is typically microseconds, and for remote attached is in milliseconds. One thing to call out here, these are usually accessible to a single instance only, and they cannot be shared across multiple instances. Now, to give you an idea of how fast such a system can be, here's some numbers from a Pinot cluster at LinkedIn serving user-facing analytics, which is currently doing 250K queries per second while maintaining strict milliseconds level latency SLAs. Okay, great. So we added a real-time analytics database, everything's super fast. We started putting all of our data into it. So what's the problem? Let's see what happens when data volume starts increasing a lot. Say you started with just one compute node with 2 terabyte storage. Assume that the monthly cost is $200 for compute and $100 per terabyte, so total $400. And now say that your data volume grows 5 times. To accommodate that, you can't just add only storage. You have to provision typically the compute along with it. So your new cost will be 1,000 for storage and 1,000 for compute. Now, if your data grows 100x, again, there's an increase in both storage and compute. More often than not, you won't need all the compute that you are forcibly adding just to support the storage that's increasing. Because increasing the storage or the data volume doesn't necessarily translate to an increase in query workloads. So you will end up paying all this extra cost just for underutilized compute. Plus, this storage tends to be very expensive compared to some other storage options available, such as Cloud Object Store. So to summarize, with tightly coupled systems, you will have amazing latencies. But as your data volume grows, you'll end up with a really high cost to serve. So we've kind of lost out on the cost aspect in our triangle. Well, now you might think, but if we need the speed for the real-time portion of the data, we gotta pay, right? Yes and no. So all data is not equal. The use cases served by real-time data and historical data are very different and tend to have different ROI. Real-time data is for real-time analytics and user-facing apps like profile views, restaurant analytics for a live restaurant service, profile analytics, and they need milliseconds latencies at hundreds of thousands of queries per second. Whereas the historical data is used for dashboards, reports, the queries per second are lower and the latency is also more relaxed. So for this historical data, there won't be enough business justification for the steep cost, and you often won't even care about the ultra low latency query performance, and you'll be more accepting of a slight latency trade-off for reducing the cost. So now how do we reduce the cost? We can take a look at a whole other category of analytic systems, such as Trino, Spark, Hoodie. These are very popular for storing and analyzing the historical workloads. These usually have a decoupled architecture, wherein the serving nodes are compute only and the data is stored on and accessed from a cloud object storage like S3. Now, let's bring this table back and see how this storage does compared to the storage that we were using for the tightly coupled systems. So this storage tends to be very cheap compared to disk and SSD. Plus, the storage is shared. It's not bound to a single instance, so your compute and storage can scale independently. But because your access now involves a network call, you lose out on latency. So naturally, these systems cannot be used for real-time data. So with decoupled systems, we traded off a lot of latency to save on cost, and now we're not looking so good on the performance aspect of our triangle. So then this is what data teams end up having to do. You add both systems, keep your recent data in the real-time database and historical in the decoupled system. But with this, you've lost out on the flexibility and simplicity aspect, as with multiple systems comes more operational overhead, more expertise, and then getting the configuration right of what goes where and how to change it. So this solution is combining the both worlds, but it is certainly not the best of both worlds. Could we somehow have a true best of both worlds, where we get the speed of a tightly coupled real-time analytics system, and use cost-effective storage like a traditionally decoupled analytics system, and yet have the flexibility and simplicity of being able to use just one system and configure it in many, many ways? With this motivation in mind, we at StarTree built tiered storage for Apache Pinot. With tiered storage, your Pinot cluster is now not limited to just use disk or SSD storage. We are no longer strictly tightly coupled. You can have multiple tiers of storage with support for a cheap cloud object storage such as S3 as one of the tiers. You can configure exactly which portion of your data you want to keep locally and which is offloaded to the cloud tier storage. So one popular way to split your data across local and cloud is by data age. So you could configure in your table config that you want data less than 30 days old to be on disk and everything else to be on S3. And then users can query the entire table across local and remote data like any other Pinot dataset. With this decoupling, now you can store as much data as you want in Pinot without worrying about the cost. And this is super flexible and configurable. This threshold is dynamic and can be changed at any point, and Pinot will automatically reflect the changes. You can still operate Pinot in fully tightly coupled mode if you want, or completely in decoupled mode, or even take a hybrid approach where some nodes are dedicated for local data and some for remote data. One important detail I'd like to call out here is that this is not to be confused with deep store or segment store. Many of you might already be familiar with the architecture of Pinot or similar systems and might know that these systems, along with the tightly coupled storage component, additionally also have a cloud object store like S3 or GCS in their architecture, which they call as deep store or segment store. However, this deep store is only used for permanent backups, disaster recovery, and is not involved in the query path. With tiered storage feature for Apache Pinot, we are now able to use this cheap cloud storage directly in the query path and replace a lot of the disk and SSDs that we were using. So to summarize, we saw that with tiered storage in Pinot, we have the flexibility of using a single system for your real-time as well as historical data without worrying about the cost spiraling out of control. We didn't talk about the third aspect yet, which is performance. Now that we're using cloud object storage, will the query latencies take a hit and enter the range of other decoupled systems? I'd now like to hand over to Xiaobing, who will take us into a deep dive of how we approached the performance aspect for queries accessing data on the cloud storage. Over to you, Xiaobing.
Thank you, Neha. As Neha explained just now, we are able to decouple the storage and compute layers for Pinot. And as you see in this table early on, the cost of cloud object storage is a lot lower than local disk or EBS. So we can use cloud storage like S3 to dramatically reduce the cost of keeping a very long-term historical data in Pinot. But Pinot has been assuming segments to stay on the local disk to run the queries very fast, because they try to memory map the segments for random data access very quickly. So to make sense work with remote segments on S3, we actually have to extend the query engine to make it agnostic to segment locations. And under the hood, we actually plug in our own buffer implementation so that during the query execution, we can read data from those remote segments transparently. But making query work is just part of the story. As we said earlier, we really want to get the best of the two worlds using Pinot, which means we have to keep the query performance of Pinot, even though the latency to access the data from cloud object storage is a lot higher than local disk, as you can find in this table. So to address this challenge, we need to think about a few questions. For example, what data we need to read, because apparently we don't have to read the whole table when we run the queries. And also how and when we need to read the data during query execution. And in the following slides, I'll try to answer those questions by explaining some design choices we have made along the way. At the very beginning, we thought about using lazy loading to reduce query latency. And by lazy loading, we mean to download the segments to the local disk when the first query comes in. And the first query will be subject to high latency because they need to read the data from remote segments. But we would keep those segments on local disk and assuming the following queries would access those directly to reduce their latency. But this idea wouldn't work very well for us because the segments to access among those queries can be very different. For example, some queries may looking for data at a very different time range with the other queries, and maybe they're just looking for data for very different user IDs. So as shown in this figure here, a table may have a huge number of segments, and with tier storage, those segments are actually put on S3 as we mentioned earlier on. With lazy loading, we can only keep a small set of segments on the local disk. And if those segments are not really used by the following query, guess what? We have to remove those and leave the disk space for the segments downloaded by the new query. And this would result in a lot of churn and downloads unnecessarily. And also use lazy loading, the P99 or P99.9 query latency could be very bad because there would always be some queries that need to download the segments. And because of this, this method is like a strict no-go for OLAP system because the user of those systems require consistent low latency. So instead of using lazy loading or similar ideas like try to cache the segments on the local disk, we start to think about how we can resolve the issue for the worst case, like when the query have to read the data from remote segments. And by solving this, we can potentially guarantee consistent and predictable low latency for all the queries. So now we know we have to read remote data, then we have to read as little as possible to begin with. And because Pinot is a columnar database, we are able to read the columns actually needed by the query and just ignore all the others. And inside a Pinot segment, we actually put all the columns in a single S3 object. And we use the range get request to just looking for the columns actually needed for the query to execute. And this idea is not new and can be found in other systems with decoupled architecture like Presto, particularly when they try to read the data files in column format like Parquet. But something to be noted here, so in this early version, we actually try to read all the index created for a column, even though not all of them are really needed to finish the query. Like in this figure here, A column region may have forward index, inverted index, range index, and even balloon filter if we actually created for this column. But if this column is only used in a query projection, and all those indexes are actually not really used to run the query. This got optimized in our newer version, but I'll save the details here, and Neha will share more details about them in the next major section. Now we know what data we need to read, and then we need to think about when to read the data. And to help figure this out, let me describe how Pinot processes a query briefly. So the Pinot broker gets a query, it passes it, and sends the passed query to multiple servers to process the data in parallel. Then it will wait the servers to return the results and aggregate those to return a final one to the user. And the figure here is actually just about the Pinot server. So the Pinot server received the passed query from broker, and then it will do a query planning based on the segments owned by the server. And the planning phase will decide the segments to be processed, and then multiple threads will be used to process them in parallel. And a single thread may actually process a few segments, and it just processes those one after another. So one quick idea about when to read the columns from a remote segment is just to wait until a thread is about to process the segment. Then we just go fetch the columns needed by the query, process it, and then just release those columns, and then head on to the next segment. And all those threads, as you can see in this figure, they just pretty much can repeat those three major steps: fetch the columns needed by the query and process those and release those. But here is an example to actually understand some drawbacks of fetching data on demand. Assume we have like 40 segments on this server and 8 threads to process them in parallel. So in general, we may need like 5 runs to process all of them. And in each round, the thread will go fetch the data, process it, and then release it. And the latency to download the data from S3 is like 200 milliseconds. And the CPU time to process the data can be a lot lower compared with this data access latency. So in general, we may end up with a query latency around 1 second. And if we actually check the CPU utilization during query execution like this, we will find that most of the threads are actually just waiting for data to be available, and the CPU cores will just stay idle. And this is less ideal. And we ask ourselves, like, could we actually decide the segments to be needed by a query a lot earlier so that we can prefetch them? In this way, we could potentially pipeline the I/O and the data processing as much as possible to reduce the CPU wait time. And the answer is yes, because during the planning phase, we can already decide the segments to be used by the query, and we can just prefetch all of them in a single batch. And the thread processing the segments will still need to wait for the data to be available. But in some best cases, the data may already be downloaded by those prefetching threads, so the waiting time, CPU waiting time, can be a lot lower in this case. So back to our simple example early on. So with prefetching, we could potentially reduce the query latency down to like a single round of S3 access. But there is a big assumption here. The memory space needs to be large enough to hold all those prefetched segments, and also the network bandwidth is supposed to be very high so that data can be transferred really quickly in addition to this round-trip request latency. However, those two are actually not always can be true in the real-world scenario. So we did a simple benchmark with our phase 1 version. To recap really quickly, in this phase 1 version, we do columnar read, and we prefetch data during the planning phase. And the benchmark was conducted in a small setup here. So with 200 gigabytes data on a single Pinot server. And the server has like 8 cores and 64 gigabytes memory. So the query we use here are mostly like aggregation queries with filters, group by, and order by. And we also included a baseline Pinot cluster with local storage, which is like the tightly coupled architecture, and Presto as a reference system with the decoupled architecture. So now let's see the numbers in the table. So overall, we can see Pinot with tiered storage was about like 5x to 20x faster than Presto. And the speedup was mainly from like the indexing techniques supported by Pinot, like inverted index, range index, or JSON index, which are very effective for the test queries here. But compared with the baseline Pinot, we still see a clear slowdown. And this showed us that the two techniques we implemented in this early version are not super effective to hide all the data access latency from S3. So to learn more from our first version, we stress tested a lot with a larger workload and a cluster setup. So basically, we try to put 10 terabytes data into a Pinot cluster with 2 servers and also enable the tiered storage. And first of all, we found that the network got saturated very often, as you can see in this Grafana figure below. So the reason is that even though we try to reduce the amount of data to be read during the query with column read, we still read a lot of data unnecessarily for those columns required by the query. For example, we get all the index created for a column, and also we try to fetch the full column in the requested segments. This is less ideal. For example, inverted index is not really needed if the column is only used in query projection. And also not all the forward values are needed after all kinds of filterings. It's very likely only a tiny part of the value need to be used to finish the query. And secondly, because of this network bottleneck, in general, the more data to fetch during the query execution, the longer the query would take, as you can see in the chart below. But however, when the network was not saturated, the query latency was mainly determined by how many rounds of data fetches were done. So when the network is not saturated, we can try maybe increase the I/O parallelism to take use of those remaining bandwidths. Another interesting finding is that the prefetching didn't work all the time, particularly when the query needs to read more segments than memory reserved for prefetching. And one major reason for that is the segment got prefetched are not necessarily those to be processed immediately, because the prefetching and processing are done by 2 independent thread pools. So this would waste the memory space and also increase the CPU wait time. And there are a few other quick takeaways we learned from the stress test. It's better to reuse the S3 connection by just pooling them, and also try to use async I/O library to avoid creating too many threads to do the data fetch. And so far, this is about our phase 1 implementation, our kind of the first version. And with those lessons we learned, I'm going to hand it over back to Neha, and she will walk us through a few new ideas we have implemented to reduce the query latency a lot further.
Thank you, Xiaobing. So the most important takeaway for us was that we needed to reduce the amount of data fetched. There are 2 stages where we can do this. One is reduce the number of segments that are processed, and secondly, reduce the data within the segment that is read. For the first part, pruning segments is already a first-class concept in Pinot. So all we had to do was make sure that we are able to utilize those techniques effectively in the new architecture. We have pruning based on min-max column values or partition info. Both of these metadata are cached locally whenever available, so we were able to quickly eliminate segments where we won't find any matching data. Another popular technique used in Pinot is bloom filters. These are built per segment, and we can read it to know if a value is absent from a segment. This is more effective than the other pruning strategies, but the problem is that it is stored inside the segment, which is now on S3. So accessing them for all segments is inefficient in this architecture. To address this, we added an advanced configuration to define how to split the data into local versus remote. You can now be super granular and say, I want this specific column to be on local, or I want the specific index of the column to be on local, and everything else on the cloud storage. With this, you could pin bloom filters locally, which is usually a very small fraction of the total storage, and then that will help us to do fast and efficient segment pruning. Now, once we know exactly which segments we want, how do we read even less within the segment? For that, we decided to add some smartness to the query planner to not blindly start prefetching all indexes. Bringing this example from Xiaobing's previous slide back, to answer this query where we have a filter on region and then some aggregations on impressions, we only need to look up the inverted index for the region. So probably we don't need to fetch anything else for the region column. After applying the filter, you might have to read very few rows within the column impressions. So probably we don't need to fetch the full forward index for impressions, and we can just read small blocks of data during the post-filter execution. We tested out these optimizations on the 10 terabyte data setup that Xiaobing was talking about earlier. So we took 3 queries of varying selectivity, and we saw some amazing reduction in data size read compared to our phase 1, which in turn improved the latency significantly. But we still weren't seeing the latency align with the 1.25 gigabytes per second network bandwidth that was available to the server, which was aligning pretty well in our baseline when we were able to saturate the network. Which meant that we now have room for more parallelism. The reason was that within the segment currently, we have no parallelism in Pinot. So any blocks we need, we are reading sequentially. And this was fine for Pinot when everything was read locally. But in tiered storage, each of these reads becomes a read to S3. So the next level of optimizations we are aiming for are, can we build some block level intra-segment bloom filters to know the exact block of data that we need? And then can we use that to execute all the matching blocks in parallel in the post-filter phase? So the work proposed in this slide is still in progress as of this recording, and we're super excited to see what numbers we get after we're done with it. And this brings us to the end of the presentation. We'd like to summarize some of the key takeaways. With tiered storage in Apache Pinot, we have unlocked flexibility and simplicity of using a single system for real-time as well as historical data. We are able to use cheap cloud object storage directly in the query path instead of disks and SSDs only, so we don't have to worry about the cost spiraling out of control as the data volume increases.
And also, we are able to get a better performance than traditionally decoupled system because we are able to effectively use the indexing techniques and some prefetching optimization and also the pruning techniques. So we are still pushing the boundaries of the performance with some new optimizations and to get closer and closer to the tightly coupled latencies.
Thanks everyone. Thanks for tuning in and hope you have a great rest of the summit.
Thank you, folks.